I'm using Gaussian process regression, a powerful machine learning technique, and I'm combining two kernels. One is a radial basis function, RBF, kernel, and the other is a linear kernel. This combination will give my model unique properties. The problem is to understand how combining an RBF kernel and a linear kernel affects the resulting model's behavior. The question specifically asks about how these combined kernels will behave in a Gaussian process regression model that uses sklearn, a popular Python machine learning library. This option suggests the combined kernel will create a model that prefers smooth functions that also have a linear trend. This option claims the model will only create linearly increasing functions, which is incorrect. This option says at large distances, the RBF's influence will be dominant. I think this is partially correct, but needs more clarification. This option claims that both kernels will have equal influence at all distances. I disagree because the RBF influence weakens with distance. RBF stands for radial basis function. It's a kernel that measures similarity and decays exponentially with distance. Think of it as a bell curve. It gives high similarity to nearby points and low similarity to distant points. A linear kernel simply models a straight-line relationship between data points. The influence of this kernel increases linearly with distance between points. I see RBF as the radial basis function kernel. It favors smooth functions. Its influence decreases exponentially as the distance between data points increases. Think of it as a blurring effect. Closer points are strongly related, further points are weakly related. The linear kernel models a perfectly straight-line relationship. Its influence is directly proportional to the distance between data points. The further apart the points, the stronger its effect. Imagine a perfectly straight-line graph. The further along the line, the larger the difference in values. This is where the magic happens. We're combining the RBF and linear kernels by multiplying them together. That means at shorter distances, both kernels contribute significantly to the prediction. However, as the distance grows, the RBF kernel's effect fades away exponentially, leaving the linear kernel with less overall effect. It's a blend that smooths the linear trend at short distances, but shows more linear influence at longer distances. This summarizes the behavior of the composite kernel. It captures the smoothness of the RBF while retaining the general linear trend provided by the linear kernel. Think of it as a slightly wavy line on a mostly straight path. I'm using Gaussian process regression, a powerful machine learning technique, and I'm combining two types of kernels: the radial basis function, RBF, kernel, and the linear kernel. Think of kernels as ways to measure similarity between data points. Combining them lets me capture both smooth, curvy patterns and linear trends in my data. I'm presented with a multiple-choice question. I need to understand how the combination of RBF and linear kernels behaves. The RBF kernel has a length scale of 1.0, which controls its smoothness, and the linear kernel has no specific parameter. This option says the combined kernel will prefer functions that are both smooth, like a gently rolling hill, and have a linear trend, like a straight line. This makes sense because the RBF kernel loves smoothness and the linear kernel loves straight lines. This option is too restrictive. The composite kernel can model other patterns because of the RBF kernel's ability to handle smooth curves. At large distances, the RBF kernel's influence weakens significantly, so this statement is incorrect. The linear kernel's effect, while still multiplied by the diminishing RBF, would become relatively more significant. This is wrong because the RBF kernel's influence decreases with distance. The radial basis function, RBF, kernel measures similarity based on the distance between points. The further apart points are, the less similar they are considered, leading to smooth functions. The linear kernel measures similarity by simply considering the dot product of the data points. It directly models the linear relationship between data points, producing linear trends. The product of the RBF and linear kernels combines their effects. At close distances, both contribute substantially. As distance increases, the RBF's influence fades, leaving the linear kernel's influence more prominent. However, Even then, the linear component is still scaled by the RBF component, which is never truly zero except at infinite distance. I'm using Gaussian process regression, a powerful machine learning technique. It uses a composite kernel, a combination of radial basis function, RBF, and linear kernels, to model the relationship between data points. Think of it as using two tools together for a more complete picture. We're analyzing how the combined RBF and linear kernels behave in a Gaussian process regression model to understand their combined effect on predictions. At large distances, the RBF kernel's influence becomes very small, almost disappearing, which makes this statement not quite accurate. The combined influence is small, but the remaining effect is dominated by the linear kernel. It's a subtle point. I'm using the radial basis function kernel, RBF. It measures similarity between data points, giving a higher score to points that are closer together. Its effect diminishes rapidly as the distance between points increases. It's like the influence of a strong magnet, powerful up close, weaker from afar. The linear kernel models the relationship between data points as a straight line. The influence of this kernel increases proportionally with the distance between the points. Think of it like a simple ruler, measuring distance directly. The product kernel combines the effects of the RBF and linear kernels by multiplying their results. This means at short distances both kernels contribute significantly, but as distance increases, the RBF's decreasing influence leaves the linear kernel with more relative, say, but still diminished by the shrinking RBF component. It's a multiplicative effect, not an additive one. I'm exploring how a combined kernel, made by multiplying an RBF kernel and a linear kernel, affects Gaussian process regression. It's like asking, what kind of functions will my model prefer? The RBF kernel measures similarity between data points. A smaller length scale means it focuses on local relationships. The similarity drops off quickly with distance. In this case, the length scale is 1.0, meaning the influence decreases moderately quickly as data points get further apart. This kernel looks at the linear relationship between data points. Its impact increases proportionally with the distance between points. The bigger the gap, the stronger its contribution to the model. I'm basically looking at how straight a line the function tends to have. This is the star of the show. It's the result of multiplying the RBF and linear kernels. I'll be looking at how the combined impact of both kernels drives the model, focusing on the trade-off between smoothness, from RBF, and linearity, from linear. This is like asking, how much does the overall model favor both smoothness and linear trends? We are evaluating statements about how a combined kernel, made from RBF and linear kernels, behaves. It's like detective work to figure out this puzzle. We're looking for the options that correctly describe the behavior of the combined kernel. At large distances, the RBF kernel's influence weakens significantly due to exponential decay. The linear kernel's influence remains present, but it is now multiplied by a very small number from the RBF, making the overall influence very small at large distances. It's not about domination, it's about diminishing importance. It's a subtle but important distinction. I'm using Gaussian process regression, GPR, which is a powerful machine learning tool, and to improve its adaptability, I'm using a composite kernel. This means I'm combining kernels, in this case, an RBF and a linear kernel, to achieve a more flexible model. It's like creating a superkernel with the best of both worlds. This statement isn't true because the RBF kernel's influence decreases as the distance between data points increases. Thus, both kernels don't have equal influence all the time. Think of it like this: the RBF kernel's voice gets quieter as you move farther away. I'm analyzing how different kernel types in Gaussian process regression interact and affect the model's behavior. I'm focusing on a composite kernel, which is the product of an RBF kernel and a linear kernel. The RBF, radial basis function, kernel measures similarity between data points. It uses a length scale parameter, here, 1.0, which controls how quickly the similarity decays with increasing distance. A smaller length scale means faster decay, meaning less similarity between distant points. Think of it as a local influence. It strongly emphasizes nearby points and less so the ones farther away. The linear kernel models a straightforward linear relationship between data points. Its influence grows proportionally with the distance between points. It's all about the trend. It highlights the overall direction of the data. We need to determine which statements correctly describe the combined behavior of the RBF and linear kernels when they are multiplied together. At large distances, the RBF kernel's influence becomes very weak because its effect decays exponentially, meaning the linear part is not particularly strong either. It would be more accurate to say the composite kernel's overall influence is small. It's not dominated by the RBF, both kernels are diminished. This is incorrect because the RBF kernel's influence decreases exponentially with distance, meaning the kernel's contributions aren't equal at all distances. This is correct. The RBF kernel encourages smoothness, while the linear kernel introduces a linear trend. The combined result is a function that's both smooth and trending linearly. I'm using a Gaussian process regression model that combines the strengths of both RBF and linear kernels in one model. This model will predict values based on a probability distribution which is defined by the combination of these kernels. The RBF kernel will provide the smoothness while the linear kernel will capture the linear trend in the data, effectively combining their individual capabilities. We see this as the core of the problem. We're combining two different kernel types. The radial basis function, RBF, kernel, which focuses on smoothness and localized relationships, and the linear kernel, which captures linear trends. Multiplying them together means their effects are combined. At short distances, both kernels contribute substantially to the model's behavior. However, as distances increase, the RBF kernel's influence weakens significantly, it decays exponentially, leaving the linear component with more say. But it is still modified by the RBF's decreasing influence. Think of it like this. The RBF is a spotlight, initially illuminating both the linear trend and any nearby deviations. As you move away, the spotlight fades, leaving the linear trend less brightly lit but still visible. It's a beautiful blend. This is the method used. We are using Gaussian process regression, a powerful technique for modeling relationships between data points. The twist is, instead of using a single kernel, we have a composite kernel formed by multiplying an RBF kernel and a linear kernel. This composite kernel combines their respective strengths. I like this choice because it will allow us to capture both smooth, local variations and overall linear trends in the data. This is short for radial basis function. This kernel creates a similarity score that decreases rapidly as the distance between data points grows. Think of it as how similar two things are. The closer they are, the more alike they seem, and the further apart they are, the less alike they appear. It has a parameter called a length scale, which controls how quickly the similarity decreases. Because the similarity score decays rapidly, it prefers smooth functions. This is one of the key players in our composite kernel. It adds smoothness and local effects. This kernel models a simple, linear relationship between data points. Its influence is proportional to the distance between the points. The farther apart, the stronger the influence. It simply reflects a linear trend in the data. In our composite kernel, this part provides the overall trend. This one is straightforward, capturing linear trends. I agree with this statement. Because we're combining an RBF kernel, favoring smoothness, and a linear kernel, favoring linear trends, the resulting model will prefer functions that are both smooth and exhibit a linear trend. It's the best of both worlds. I disagree with this. The RBF kernel's influence diminishes with distance. Therefore, both kernels cannot equally influence the model at all distances. At larger distances, the linear component becomes more influential, however it is still modulated by the RBF. I think this is slightly misleading. At very large distances, the RBF component is near zero, making the linear component very weak as well, since it is multiplied by the near zero RBF component. So, neither component actually dominates at large distances. The composite kernel's overall influence becomes insignificant. A more precise statement would emphasize the diminishing influence of both kernels at large distances. I disagree. The presence of the RBF kernel allows for nonlinearity and smooth variations around the linear trend. So, it can model other nonlinear behavior as well.